Welcome back. I'm not going to do a bunch of projectile motion problems, just because I think you'll learn more just seeing someone do it and thinking out loud maybe than all the formulas. And I have a strange notion that I might have done more harm than good by confusing you with a lot of what I did in the last couple of videos. So hopefully I can undo any damage if I have done any, or even better, hopefully you did learn from those, and we'll just add to the learning. So let's start with a problem. Well, let's just start with a general problem. Let's say I'm at the top of a cliff and I jump. So instead of throwing something, I just jump off the cliff. And we won't worry about my motion from side to side. We just assume I go straight down. You could even think that someone just dropped me off of the top of a cliff. And I know these are getting kind of morbid, but let's just assume that nothing bad happens to me. So let's say that at the top of the cliff, my velocity, so my initial velocity initial is going to be 0, right? Because I'm stationary before the person drops me or before I jump, right? And let's say at the bottom of the cliff, my velocity is, let's say it is 100 meters per second. So my question is, what is the height of this cliff? So what is, and actually, you know what? Let me. I think this is a good time to actually introduce the direction notions of velocity that show you the scalar quantity. So let's just assume up is positive and down is negative. So my velocity is actually 100 meters per second down. I could have assumed the opposite. So the final velocity is 100 meters per second down. And since we are saying that down is negative and gravity is always pulling you down, we're going to say that our acceleration is equal to gravity, which is equal to minus 10 meters per second squared. And this is, gravity. I just wrote that ahead of time just because when we're dealing with anything of throwing or jumping or anything on this planet, we could just use this constant. And the actual number is like 9.81, but I want to be able to do this without a calculator, so I'll just stick with minus 10 meters per second squared. So it's pulling me down. That's why the minus is there. So my question is, okay, I know my initial velocity, I know my final velocity right before I hit the ground, or right when I hit the ground. What's the distance? And in this circumstance, what does distance represent? Distance, it would be the height of the cliff. So how do we figure this out? Well, what's the only formula that we know for distance? Well, we know that actually it's really the change in distance, but in this case it's the same thing. So change in distance is equal to the average velocity. And when you learn this in middle school or wherever, or probably even elementary school, you didn't say average velocity because you always assumed velocity was constant. So the average and the instantaneous velocity was kind of the same thing. But now, since the velocity is changing, we're going to say the average velocity. So the change in distance is equal to the average velocity times time. And this should be intuitive to you at this point. I mean, velocity really is just distance divided by time, or actually change in distance divided by times change in time. Change in distance divided by change in time is velocity. So actually, let me change this to change in time. Right. But since we always assume, or we normally assume, that we start at distance is equal to 0, and we assume that we start at time is equal to 0, we can write distance is equal to velocity average times time. Maybe later on we'll do situations where we're not starting at time 0 or distance 0, and in that case we will have to be a little more formal and say change in distance is equal to velocity, average velocity times the change in time. Sorry, I'm messing up all the terminology. But anyway, this is the formula we know. And so let's see what we can figure out. Can we figure out the average velocity? Well, the average velocity is just the average of the initial velocity and the final velocity. So the average velocity is just equal to the average of these two numbers. So minus 100 plus 0 over 2. I'm just averaging the numbers. Equals minus 50 meters per second. So we were able to figure that out. Well, can we figure out time? Well, we know also that velocity, or let's say that change in velocity, so change in velocity is equal to the final velocity minus the initial velocity. right? Nothing fancy here. You don't have to memorize this. This hopefully is intuitive to you that the change is just the final velocity minus the initial velocity, and then that equals acceleration times time, right? So what's the change in velocity in this situation? Well, the final velocity is minus 100 meters per second, and then the initial velocity is 0. So that equals, the change in velocity is equal to minus 100 meters per second. I'm kind of jumping in and out of the units, but I think you get what I'm doing. And that equals acceleration times time. Well, what's the acceleration? It's minus 10 meters per second squared, because I'm going straight down. Minus 10 meters per second squared times time. This is a pretty straightforward equation, right? Divide both sides by the acceleration, by the minus 10 meters per second squared, and you will get time is equal to, the negatives cancel out, and as they should, because, well, right, negative time is a difficult, well, we're assuming positive time, and it's good we got a positive time answer. But the negatives cancel out, and we get time is equal to 10 seconds. So there we have it. We figured out time. We figured out the average velocity. So now we could figure out the height of the cliff. The distance is equal to the average velocity minus 50 meters per second times 10 seconds. So the distance, and this is going to be an interesting notion to you, the distance is going to be minus 500 meters. So this might not make a lot of sense to you. What does minus 500 meters mean? Well, this is actually right, because it's actually, this formula is actually the change in distance. Change in distance, right? We said if we did it formally, it would be the change in distance. So if we have a cliff, let me change color so that it looks like a cliff. So if we have a cliff, and if we assume that we start that this point right here is distance is equal to 0, then the ground, if this cliff is 500 meters high, your final distance, so this is the initial distance, your final distance, df, is actually going to be at minus 500 meters. Right? We could have done it the other way around, where we could have said this is plus 500 meters and then this is 0. But all that matters is really the change in distance, right? We're saying from the top of the cliff to the ground, the change in distance is minus 500 meters. And minus, based on our convention, we said minus is down. So the change is 500 meters down. And that's the height of the cliff. So that's pretty interesting. If you go to a 500-meter cliff, so that's what? That's roughly the size of a, let's see, 500 meters is about 1,500 feet. So that's roughly the size of, maybe a very tall skyscraper like the World Trade Center or the Sears Tower. So if you jump off of something like that, assuming no air resistance, which is a big assumption, or let's say if you were to drop a penny, because a penny has very little air resistance. If you were to drop a penny off of the top of a Sears Tower or a building like that, at the bottom it will be going 100 meters per second, so extremely fast, and that's why you shouldn't be doing it, because that is fast enough to kill somebody. And I don't want to give you any bad ideas if you're a bad person, but it's just interesting that physics allows you to solve these types of problems. So in the next presentation, I'm just going to keep doing problems, and hopefully you'll realize that everything really just boils down to average velocity, change in velocity is acceleration times time, and change in distance is equal to change in time times average velocity, which we all did just now. So I'll see you in the next presentation.